Welcome to my video course on engineering FRMCS. Today, we're unpacking a really fascinating and honestly core engineering challenge. How exactly do we integrate a massive variety of traditional railway applications into a brand new shared 5G telecommunications ecosystem? I mean, this isn't just your standard IT upgrade, right? It's the central puzzle of the future rail mobile communication system.
Just think about the sheer scale of a modern train operation for a second. How on earth do dozens of wildly diverse train applications share a single 5G network? On one hand, you've got absolutely critical train control and safety systems like the European Train Control System that ensure trains literally don't crash into each other. If that connection drops, trains have to come to an immediate halt, zero room for error. But then, on the other hand, you've got systems like basic voice communications for drivers, automatic train operation data, or even onboard video surveillance. If a voice call drops, well, it's annoying for sure, but it's not a catastrophic failure. Yet they all need to use the exact same underlying 5G FMCS infrastructure. If we look at this from a systems engineering perspective, treating all these systems equally is just a recipe for massive complexity and severe safety risks. They need dedicated rules of engagement.
Okay, let's dive into this. Here's our roadmap for this session. We'll start by mapping out the application ecosystem so we can really understand our boundaries. Then we'll define the different coupling regimes. From there, we'll look at how this plays out in the real world. Tight-coupled voice systems, loose-coupled safety systems like ETCS, and finally, super loose-coupled setups for legacy tech. We'll wrap the whole thing up with a quick architectural summary. Let's get right to it.
So, Part 1. The FMCS Application Ecosystem. Before we can even think about connecting different systems together, we have to establish where our architectural boundaries actually lie.
You see, the FMSC's architecture is strictly separated into what we call strata, or functional layers. At the very highest level, we have the application stratum. This encompasses all railway applications, both onboard and trackside. But here's the absolutely crucial detail. This stratum sits entirely outside the telecom network itself. It's completely separate from the service and transport strata. Think of the telecom network as the plumbing hidden in the walls of a house and the applications as the sinks and showers you actually use. They are totally separate entities. And the coupling boundary dividing them, well, that's precisely what dictates our engineering rules today.
This brilliantly illustrates those physical and logical boundaries we just talked about. Notice those vertical lines marked OB-app on the left and T-app on the right of the end-to-end path. OB-app is the onboard application reference point, and T-app is the trackside equivalent. These aren't just conceptual lines on a drawing. They are hard, logical boundaries separating the railway applications from the core FRCMS infrastructure system in the middle. Exactly how an application crosses those specific boundaries changes its entire design. Basically, it defines how intimately the train hardware interacts with the cell towers.
Moving on to Part 2. Now that we've mapped out those physical and logical boundaries, let's figure out how different applications actually cross them and plug into the architecture. We can actually categorize these connections using a really straightforward matrix. The designated coupling mode of any application depends entirely on one critical question. Where does the FRCMS service client live? You can think of this client as the software agent that actually knows how to speak the 5G network's language. If this client lives inside the application itself, boom, it's tight coupled. If the application delegates this job to a client located entirely inside an FRCMS gateway, then it's loose coupled. And if it relies on that gateway but actually needs an extra external proxy agent just to translate its outdated signals, we call that a super loose regime.
Okay, let's bring this to life with Part 3 and look at our first real-world implementation: tight-coupled voice applications.
In a tight-coupled regime, the FRMCS service client is housed directly inside the application. Because of this, the application environment actually reaches across that boundary we mentioned, right into the service stratum. These applications are native speakers of the 5G telecom network. They independently handle 3GPP mission-critical, or MCX, service primitives, managing their very own session initiation protocol requests. The textbook example here is voice communication. When a driver initiates an ad hoc emergency group call to a dispatcher, that radio application is directly, natively negotiating its connection with the 5G network. It doesn't need a translator at all. It just connects.
Now for Part 4. Let's contrast those native voice systems with our loose-coupled regimes like ETCS and ATP, where strict network independence is a non-negotiable safety requirement.
Now, what's really interesting about this contrast is the strict isolation. Voice applications are completely telecom dependent.
They directly access the network using those MCX primitives. But compare that to automatic train protection systems like ETCS. These absolutely vital systems are strictly telecom independent. They do not directly manage network sessions. Instead, they remain safely isolated behind an API gateway, totally protected from the unpredictable mechanics and upgrades of the underlying 5G network.
So, for loose-coupled applications, the FRMCS service client is relocated into the gateway. The application simply hands off its data using a standardized API at that OB app or TS app boundary. The gateway essentially acts as a dedicated translator. It takes local API requests and spins them into complex 5G network signaling on behalf of the application. This kind of strict isolation is brilliant for systems like ETCS Level 3 moving block implementations. It allows the train's engineering computer to focus purely on what it does best, calculating train location integrity and movement authorities while leaving the messy business of routing 5G sessions entirely to the telecom engineer's gateway.
Section 5. We've seen native apps and we've seen API-aware apps. But what about super loose-coupled applications? How do we handle legacy systems that don't even know what an FRMCS API is?
Hey, if you look at the super loose application regime here, notice the connection pathway. Before an external application's data ever even reaches that OB app or TS app boundary line, it is intercepted by an agent. This crucial agent block sits precisely between the FRMC's gateway and the totally unaware external application, acting as a mandatory middleman.
Let's break down step by step why this flow is so incredibly vital. You see, railway hardware is often designed to last 30 or 40 years, right? While telecom networks evolve maybe every decade. In a super loose regime, the legacy application operates entirely unaware of modern FRMC's interfaces. It doesn't even speak the gateway's API language. So a third-party proxy agent is deployed to intercept the application's legacy traffic. The agent then translates and implements the required API primitives on behalf of that application. Finally, the FRMC's gateway processes that connection to the service stratum. It is just an incredibly elegant engineering workaround to future-proof decades-old train hardware against rapidly shifting 5G standards.
Moving to Section 6, let's start wrapping this up and synthesize all these distinct engineering principles into a concise architectural summary.
Ultimately, these strict boundary rules exist to solve our initial puzzle, ensuring the safe, shared usage of radio access resources for wildly different concurrent applications. Tight coupling optimizes for speed and native capabilities, which is perfect for voice. Loose coupling provides the strict telecommunication independence necessary for life-critical train protection like ETCS. And super loose coupling bridges the gap for older, interface-unaware legacy systems. By standardizing these connections at the boundaries, the centralized FRMCS gateway can manage incredibly complex tasks, like multipath routing across different modems or seamless network handovers, completely transparently, without ever disrupting the applications relying on it.
So the choice of coupling regime is a deliberate engineering decision based on a careful balance, an application's need for direct network control versus its need for strict isolation. So I leave you with this provocative question to consider for your own projects. Which coupling regime will you choose when architecting your next trackside application? Thanks, we can see you next video.